Many, many thanks, Professor Kuhn, for that very generous introduction. And my thanks to those who have made it possible, a very special honor for a historian of science, to address you in the Accademia dei Lincei. May I please have my PowerPoint presentation? Okay. Yep, great, thank you. So a historian of science among scientists often feels compelled to justify her very existence in a society which is saturated with science and science-based technology. It certainly seems obvious that the general public, all of us citizens, need to learn something about how modern science emerged, how it became intertwined with technology, and under what social and political conditions it flourishes or withers. Historically speaking, it's very much the exception rather than the rule for a society to support research, scientific research, which has, in some cases, very little prospect of immediate practical payoff. One recent example would be this marvel of ingenious engineering, the James Webb Telescope, Space Telescope, which had an enormous price tag and has sent back stunning photographs of the cosmos, will at some point tell us a great deal about the formation of stars and distant galaxies, but has very, very little prospect of changing anything on this planet, at least in the middle term. This is especially important, this understanding of the history of science is especially important for citizens of democracies in which at least 90% of scientific research is funded by the public purse. We need to understand how science developed in the past and how it works in the present in order to make informed decisions about which research deserves support, and also why sustained support for research is so vital to any modern society, even when resources are scarce and election cycles are short. But that doesn't answer the question of why scientists need the history of science. After all, science is focused not on the past, but on the future, on the next new discovery, the next new theoretical breakthrough. It is true that scientists sometimes pay tribute to their own pantheon of scientific gods and demigods. This was for the chemists in the room. This is the facade of the Massachusetts Institute of Technology, Killian Court, dedicated to the pantheon of chemists. Scientists may revere this pantheon of great past scientists, and they might even read biographies of the likes of Galileo or Darwin or Einstein or Lavoisier, but they rarely cite literature more than 5 years older in their own publications. So what use is the history of science for science right now? There's a contradiction at the heart of modern science that the history of science can help to resolve. Scientific knowledge is, I think, indisputably the most reliable knowledge that we have, but it is not the eternal, unchanging truth of the philosophers and the theologians. At precisely the moment when a branch of science is advancing by leaps and bounds, it's also leaving behind what we thought we knew in a cloud of dust. And the scientific past can suddenly once again become urgently relevant. Lines of investigation which have lain fallow for decades, sometimes for centuries, may suddenly bear fruit and overturn long-held scientific orthodoxies. Just one example. These are glass photographic plates taken around the year 1900 in one of those large international collaborative projects, the Carte du Ciel, the great astrophotographic map of the sky. They were gathering dust in the observatories of the world for about 100 years when, like Sleeping Beauty, they were awakened in the 1990s because they provided important evidence for the existence of dark matter. Moral, never throw anything away. or a theory that had delivered wide-ranging explanations and astonishingly precise predictions for centuries, even such a theory can be overturned in the space of a few years, as Einstein's theory of general relativity overturned celestial mechanics in the early 19th century. New discoveries may be celebrated with Nobel Prizes. Textbooks may turn discoveries into doctrine taught to graduate students. Historians of science may award laurels to the winners in the race to discover radium or figure out protein structures or predict the existence of black holes. But eventually, and this is the secret that all scientists and scholars know, eventually, all will have to be revised in light of new achievements, discoveries, and predictions. Because science advances, the history of science will not stay written. So the price of scientific progress is impermanence. If there's one lesson to be learned from the history of science, it is that whatever scientific truth might be, it is dynamic. It's more like the flowing river of Heraclitus than the eternal forms of Plato. It's the business of philosophers to sort out conceptual contradictions like the one between scientific progress and Platonic ideals of truth. Scientists generally have little time or patience for puzzles that admit of no empirical solution. But occasionally, scientists too have to confront this uncomfortable contradiction between the fact of scientific progress and the ideal of scientific truth, especially when they are called upon to explain to us, the general public, why today's scientific truth has discarded yesterday's scientific error. We all experienced this recently in real time during the SARS-CoV-2 pandemic. It's only the most recent example of scientists thrust into the limelight of media scrutiny and asked about what the virus was, how it spread, and what could be done to mitigate disease and death. Disconcertingly, the scientists' answers to all these questions seem to change on a weekly basis. New observations by clinicians, new experiments in laboratories, new results of clinical trials corrected, contradicted, or simply confused the old answers to these questions. Governments counseled citizens to follow the science, but following the science left everyone breathless, including the scientists themselves. At such moments, even scientists are forced to ponder the implications of scientific progress for scientific truth. Much of my work in the history of science has been an attempt to understand the nature of scientific progress and its deep implications for how we live and how we think. I believe that the long perspective provided by the history of science can answer, or at least help to answer, the stark question posed by many people, including many scientists, and not just during a global pandemic. Can scientific progress coexist with scientific truth? Science is one of those suitcase words that beg to be unpacked, and it contains a multitude of different disciplines. Each of these disciplines not only has its own subject matter, it has its own methods of inquiry, its own standards of evidence and proof, and its own criteria of success. The physicists who work on elementary particle physics at CERN can predict the behavior of these particles with astonishing precision. In contrast, their colleagues who are working on phenomena of turbulence, for example, the global climate system, face challenges of complexity that boggle even the most high-speed computer and the most sophisticated mathematical models. So we've got to keep in mind such crucial differences in methods and standards when there are public pronouncements about science in general. And we're also not done unpacking the science suitcase. There are also important distinctions to be made about how we talk about scientific progress, which can be imagined either as a cathedral being built brick by brick over generations or even centuries, or we can imagine it as a speeding locomotive, as a vertiginous ride to who knows where. And since the 19th century, scientists have used both of these metaphors, sometimes even in the same sentence. So the history of science, I think, can, by expanding the timeline of scientific development beyond the present moment, help us understand how these two very different images of scientific progress can coexist with one another. So let's imagine that science clocks ticks according to two clocks. And at this point, I'd like you to recall the beautiful duet with which this session opened, and to remember the very different tempi played by the violin and the cello. The fastest of these clocks, which is running at allegro tempo, times the pace of empirical discoveries. So from the first scientific journals of the 17th century to the latest issue of Science and Nature, these are the novelties from the laboratory, the observatory, the field, which succeed each other at breakneck speed. Okay, so that's the first clock. The second clock, which seems to have gotten, yes, there we go. The second clock is progressing at a stately andante. It tracks the emergence of significant new theoretical frameworks, which we often abbreviate with the names of those who first formulated them. Aristotle, Newton, Einstein, Watson, and Crick. This second clock is proceeding at a pace not of weeks and months like the first clock. It is proceeding more at the pace of decades and even centuries. The third clock is going even more slowly. It is going at a glacial largo tempo. This is the accumulation of ways of knowing so fundamental to science that they seem self-evident. Practices like experimenting in a laboratory, observing at an astronomical observatory, finding correlations, mining data, simulating with computers. This is, and think of the cello line in the duet, this is the basso continuo of science, which unfolds over centuries and sometimes even millennia. It's on this scale, this slow, slow scale, that the ideals and practices of what it means to do science emerge, what it means to know and how to go about knowing. So at any given moment, a given science may be gripped by novelty at any one of these three levels of change. During the SARS-CoV-2 pandemic, for example, new empirical results in virology and immunology accelerated from allegro to prestissimo, to the point where even online preprint servers buckled under the volume of submissions. So that was the allegro level. At the andante level, theoretical deliberations about how to sift through all of these results produced in haste and not all equally reliable, which inferences to draw from them and how to make them cohere with each other and with what was previously known about coronaviruses. This is still ongoing, and it's likely to take years. So imagine that you're in a position of having a jumble of jigsaw puzzle pieces, and not only do you have to reconstruct the puzzle, the picture of the one completed jigsaw puzzle, you don't even know if all of the pieces belong to the same puzzle. That's the situation that the scientists who are trying to sort out all we learned at allegro tempo are proceeding at the andante level of developing a theoretical understanding of the phenomenon. And at the slow largo level, there's the immense challenge of squaring three ways of knowing in the biomedical sciences. One of them is ancient, captured in this ancient Greek vase depiction of Hippocratic medicine. That's clinical observation. The second is perhaps just about a century old, developed by Ronald Fisher in the 1920s, randomized clinical trials. And one is brand new, data mining, developed within the last decade or so. The challenge is, how do you integrate all three of these ways of knowing, which developed under different historical circumstances to solve different kinds of scientific problems, but all of which have to be brought to bear on a problem like the SARS-CoV-2 pandemic. So it's in precisely situations like this that the two narratives of scientific progress, the speeding locomotive and the cathedral, collide. So the locomotive model is a good fit for the allegro tempo of the latest empirical results, each hot off the press, some apparently contradictory, and none yet digested into a theoretical scheme that can weed out likely artifacts or irrelevances or make sense of what remains. But at the andante level of scientific change, remember the jigsaw puzzle, the pieces of the puzzle are being mulled over, matched, and sometimes discarded. This is slow, painstaking work, and it's unlikely to attract a reporter to the lab, so we don't hear a great deal about this kind of very important but not so dramatic developments in science. It doesn't capture headlines. It's a stumble-blunder process fraught with failure and controversy. One scientist's promising pattern, maybe another's fata morgana. This is a narrative that's going to unfold over many years with innumerable dead ends and blind alleys, and which rarely concludes triumphantly in a Nobel Prize ceremony. So it's a narrative that only a historian of science could love. But when the puzzle solving succeeds, and there is no guarantee that it will succeed, the results are not only more durable than those splashed across weekly covers of Science and Nature, they also act as a sieve for the pieces of the puzzle that turn out to belong to another puzzle, often one not even recognized to be a puzzle until decades later. So if we trained our attention at this andante level, the overall impression would be of greater durability of results, if not of eternal truth. Sooner or later, however, the bill for empiricism will once again come due. Does the third Largo level of scientific change rescue those eternal truths from the uncertainty inherent in all empirical inquiry? Its results are certainly more cumulative than those at the allegro and andante level. So once you acquire a way of knowing, like the controlled experiment, such a way of knowing is rarely abandoned, but it can be marginalized, as, for example, randomized clinical trials and data mining in biomedicine are increasingly marginalizing clinical observation. But marginalization does not necessarily mean abandonment. Take the case of AIDS, in which doctors first noticed a strange constellation of symptoms in some of their patients. These were clinical observations. Or take the case of what is happening in much of social science these days, in which large quantitative surveys, statistical surveys, are increasingly marginalizing ethnographic studies. However, the ethnographic studies are the keys to providing causal mechanisms for the statistical correlations. Take the case, for example, of the observed correlation in quite a few countries between the internet and the decline of teenage pregnancies. Only ethnographic research can supply us with clues as to what's really going on causally. So these ways of knowing are certainly more long-lived than either the andante or the allegro tempi of science. But they are not the eternal truths of philosophy. They are ways of how to conduct inquiry. They do not ensure that the results of that inquiry will endure forever. The end result, whatever it is that only some of the possible errors have been eliminated. So let me conclude. There is a good news and a bad news conclusion to the story. The good news is that there is a plausible version of progress at the Allegro, Andante, and Largo levels of scientific change. We know ever more about many, many more things. We understand more about their causes and effects, and sometimes we also understand how to manipulate both causes and effects to our advantage. And we are inventing new ways of knowing, of which data mining and computer simulations are only two examples. So depending on what level you decide to focus on, which clock you decide to observe, the narrative of progress looks more like the vertiginous version, Allegro, or the cumulative one, Largo, with Andante somewhere in between, just as in music. And just as in music, scrambling these three levels, not holding them distinct, creates cacophony or confusion or worse. The bad news is that none of these three levels produces certain immutable truths. Knowledge that is reliable, knowledge in the sense of being able to bank on it, and illuminating in the sense of deepening our understanding, is not necessarily the same thing as eternal truth. The history of science and technology abounds with examples of knowledge sturdy enough to support workable technologies and insightful enough to connect apparently disparate phenomena. But it is knowledge that is eventually displaced all the same. Just how durable scientific knowledge proves to be is highly variable, determined both by its level, Allegro, Andante, Largo, and historical contingency. For example, the degree to which cultures are willing to encourage and support research. Progress may bring improvements, but it may also bring trade-offs. For example, machine learning programs applied to big data may yield more accurate predictions for some phenomena, but at the price of obscuring their underlying causes. What kind of improvement is valued most in predictive accuracy, explanatory depth and breadth, in practical applicability will define the direction of scientific progress. But whatever the direction, whatever the successes, progress in and of itself cannot secure the immutable truths that have so long been the standard against which all knowledge has been judged, including scientific knowledge. I'll end with a question. Does science really need that kind of truth? The ideal of certain eternal truths originated in philosophy, partly inspired by mathematics, and it became entrenched in some versions of theology. This ideal is incompatible with systematic empirical inquiry, both with its intrinsic uncertainty, but also with its progressive character. Yet the empirical progressive knowledge produced by science is, even by philosophical accounts, the very best knowledge we have. If philosophical ideals of truth can't do that kind of knowledge justice, so much the worse for those ideals. The conclusion to draw from the restless impermanence of scientific knowledge is not that progressive knowledge can't be true knowledge, but that we need a better way of talking about truth. Thank you.